of a function f over a function g, hey, that rhymes. If that goes to either 0 over 0 or plus or minus infinity over infinity, then the original limit is equal to the limit with the same x going to c of the derivative of the top over the derivative of the bottom. So just as a review. So I want to talk a little bit before we get started about what these are. These are what we call indeterminate forms. There are only two types of indeterminate forms. We have more types of indeterminate forms. Some other indeterminate forms. So some other ones are 0 times infinity. So if you do the direct evaluation, you get 0 times infinity. This is an indeterminate form. Another one is 1 to the infinity. Another one is 0 to the 0. And another one is infinity to the 0. And another one is infinity minus infinity. Hi, Alfonso. Oh, let me hit record.
I've been recording.
Okay.
We're just going over L'Hopital's, Alfonso. We just got started, so.
Yes, so L'Hopital's rule, as a reminder, is if the limit as x approaches c of f of x over g of x goes to 0 over 0 or plus or minus infinity over infinity, then the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of the derivative of f divided by the derivative of g. Okay, and yeah, we just got started. So these 0 over 0 and plus or minus infinity over infinity are what we call indeterminate forms. There are other types of indeterminate forms. For example, 0 times infinity, 1 to the infinity, 0 to the 0, infinity to the 0, and infinity to minus infinity. So all these indeterminate forms basically just mean we can't really tell what's happening in the limit because these are extreme cases. When things are multiplied by 0, they go away, right? Anything times 0 is 0, but anything times infinity, well, infinity is not a number, but it gets larger and larger and larger. So we would expect it to get bigger and bigger. So these are kind of like at odds, right? This is getting, going to 0, and this is getting larger and larger. Same thing here. 1 is staying the same, but it goes to infinity. Like we take powers of infinity. So basically, these are called indeterminate forms because we cannot determine what the limit is when we have a form like this. Okay. So L'Hopital's rule only works for these two forms, but usually, or a lot of times, you can, if you get one of these forms, you can turn it into one of these forms, and we'll see some examples of that. Here are your steps for doing this. So step 1, steps for evaluating with L'Hopital's rule. Step 1, try direct evaluation. Don't try. Direct evaluation is a fancy word for you plug everything in, right? So in this case, I would plug in C every time I see an X, and then I would evaluate it. So try direct evaluation. Your second step Let me put this below. Your second step is going to be see if you get an indeterminate form. Or you might just get the solution. Step 3, if you get an indeterminate form, and if it's 0/0 or plus or minus infinity over infinity, use L'Hopital's rule. So if you get a different indeterminate form, try to rearrange how the expression looks. To then get a form 0/0 or plus or minus infinity over infinity, and then use L'Hopital's rule. And then step 5, repeat if you need to, or just repeat. Okay, so let's see an example of this. I don't know if spelling it out like this is helpful. When things are written like this, it is helpful for me personally, so I just wanted to put that here. I will make this available to you, this document. I don't know when though. I don't know when Ms. Rose will be able to upload it, but you will have it. Okay. Oh, there's stuff in the chat. Am I missing anything?
I'm answering.
Is there a formula? Yeah. So let's see some examples. To start, let's do the limit as x approaches 0 of sine of x over x. Okay, so step 1, try direct evaluation. So let's see. Sine of 0 over 0. Well, sine of 0, if you remember, is 0. So we have 0/0. What this tells us is use L'Hopital. From now on, I think I'm just going to put L'(H). Is that okay as a shorthand for L'Hopital? Just a lot less to write. So we're going to use L'Hopital's rule. So we take the derivative of the top. Derivative of sine of x is cosine of x. We take the derivative of the bottom. Derivative of x with respect to x is 1. And then now by L'Hopital's rule, we know that the original limit is equal to this new limit with the same value, 0. We take, instead of sine x, we want its derivative, cosine x. We want, instead of x on bottom, we want 1 on bottom. Okay, and then we try direct evaluation again. So now we get cosine of 0 over 1. Well, cosine of 0 is 1. 1 over 1 is 1. Okay, very quick, I know. Can I get a 3, 2, 1 in the chat just to see if we can move on to a new? Okay, great. Love it. Thank you so much. You guys are so quick. All right, so I have some more warm-up ones. I'm going to leave this up to you guys since there's only 2 of you. Do you want to do some practice yourself, and then we can go over them quickly? Or do you want to do a few together to kind of warm up and then go into some more challenging ones? Because I came with challenging ones, okay? Okay. So another example, polynomials. Let's try one of those. So the limit as x approaches 1 of 5x to the fourth minus 4x squared minus 1 over 10 minus x minus 9x cubed. When we plug in 1 for all these x's, right, 1 to any power is just 1. So we get 5 minus 4 minus 1 over 10 minus 1 minus 9. Well, that's 0 over 0. So you can use L'Hopital's rule. We take the derivative of the top. All right, this is just a bunch of power rules. So the power comes down. We have 5 times 4 is 20, and then we decrease the power. We have 2 times 4 is 8, and we decrease the power. And then the derivative of a constant is 0. We do the same for the bottom. We want its derivative. Derivative of a constant is 0. Derivative of negative x is negative 1. And the derivative of negative 9x cubed is negative 27x squared, right? Power rule of 3 times 9 is 27. Decrease the power. Okay, so by L'Hopital's rule, we know that the original limit is equal to this new limit with the same, what is that called? The same value x is approaching, I don't remember what it's called. Of instead of the numerator, we want the numerator's derivative, so 20x cubed minus 8x. Instead of the denominator, we want the denominator's derivative. And then we try direct evaluation again. So again, when we plug 1 in and we take its power, it's going to be 1. So we have 20 minus 8 over negative 1 minus 27. 20 minus 8 is 12. Negative 1 minus 27 is negative 28. And that simplifies to 3/7. Okay, so I mean, there are other ways to solve this limit, but I think L'Hopital's rule is a pretty nice way to do these. Okay, so again, we saw 0 over 0. We said, hey, that means L'Hopital's rule. We took the derivative of the numerator and the denominator, and then we created a new limit that is equal to our original one, with instead the numerator's derivative divided by the denominator's derivative. And then we just did a direct evaluation again and got a number. So we don't need to do anything else. We are done. If we get an exponent, we can use a log to get, yeah, so we'll go over one of those in a minute. Okay. Okay, so I'd say maybe let's do another couple of the more simple ones. So this time we want limit as x goes to infinity of e to the x over x squared. Okay, so let's try direct evaluation. We get e to the infinity over infinity squared. Well, e raised to the infinity, we're multiplying e by itself a bunch of times. E is bigger than 1. So we're getting bigger and bigger and bigger and bigger and bigger. So that's infinity, infinity squared, infinity. Hey, let's use L'Hopital's rule. We take the derivative of the numerator. Derivative of e to the x is e to the x. we take the derivative of the denominator, and that's just power rule. And by L'Hopital's rule, we know that our original limit is equal to limit as x approaches infinity of e to the x from here divided by 2x. Okay, we try direct evaluation again. We get e to the infinity over 2 times infinity, which is just infinity over infinity. What do? L'Hopital's rule, yet again. Derivative of the numerator is still e to the x. It's just going to keep being e to the x. Derivative of the denominator is 2. And by L'Hopital's rule, we know that this limit is equal to a new limit. The limit as x approaches infinity of e to the x divided by 2. And finally, when you plug this in, you get e to the infinity over 2, which is like infinity over 2, which is like infinity. Okay, so this limit does not exist. It goes to infinity. Just semantics. We wouldn't say, or that's not the right word. We wouldn't say the limit is infinity. We would say the limit approaches infinity and that it does not exist because there is no limit. It just keeps going. Yeah, good tip. We always take the derivatives of the numerator and the denominators separately. And sometimes, as we saw here, you need to use L'Hopital's rule more than once. Okay. Try to identify early if you're going to need to keep doing it over and over again forever, because that will not help you. If you have e to the x on top and, well, we'll see an example. We'll see an example. Okay, how are we feeling? 3, cool, 3. Okay, I'd say maybe we can do a more difficult one. Let's try it. Mr. Bay, do you want to switch about 11? Or 11:05 or something?
That works.
Whoa, okay. Okay, let's do the limit as x approaches negative infinity of x times e to the x. Okay, so when we try direct evaluation, we get negative infinity times infinity. So is this infinity? Is it negative infinity? What is it? I don't really know.
It's
Maybe.
times 0, right? Negative infinity times 0.
Thank you. I knew that didn't look right.
And by the way, Alfonso, this is one of those main tricks that you use in L'Hopital's. So if you want that list of tricks I was talking about, pay attention to this one.
Do we still have class? This week? We're off this week too. Okay, so thank you, Mr. Bay. Yeah, so we have negative infinity times 0. This is one of those indeterminate forms, but it's not 0 over 0 and it's not infinity over infinity. So this is indeterminate. And our strategy, indeterminate form. Our strategy for dealing with these is try to rearrange it so that you get to 0 over 0 or infinity over infinity. That was step 2, I think, above, or step 3. So we have a couple options for rearranging it. Of course. Happy to be here. We have some options for rearranging it. This is kind of what, I don't think people call this, but I've been calling it the flip. So it's a trick for doing this. Try to put one of these terms in the denominator. Or term is not the right word. Put one of these pieces in the denominator. So in this case, that would be either x or e to the x, right? These are the things being multiplied together. So we have 2 options. There is a way that's going to help, and there's a way that's not going to help. So let's look at, well, I don't want to say which one's which first. So let's try the flip on x. So let's put the x in the denominator. So if I want to move this to the denominator, that is the same as dividing by dividing by 1 over x. Okay, these are completely equivalent, right? Any questions on that part? No. Okay. Javi, you doing okay? Yeah. Okay, so let's try it. Try direct evaluation. We get e to the negative infinity divided by 1 over negative infinity. Well, e to the negative infinity goes to 0. 1 divided by negative infinity. Well, we have a small number on top and an ever-growing number on bottom. It's getting bigger and bigger and bigger. So the larger the denominator, if we keep the numerators the same, that's going to go closer and closer to 0. So we have 0 over 0. Let's try L'Hopital's rule. We take the derivative of the top. We take the derivative of the bottom. So the derivative of 1 over x is the same as the derivative of x to the -1, just another way to rewrite this. And now we can use power rule. So we bring this out front, and then we decrease the power. And if you want to rewrite this again, that's -1 over x squared. So by L'Hopital's rule, this is the same as the limit as x approaches negative infinity of e to the x divided by -1 over x squared. And then we try direct evaluation again. No surprises in the numerator, right? It hasn't changed. Okay, still 0 on top. We got -1 divided by infinity. That's the same case as before, really. So we use L'Hopital's rule again. Derivative of the top is going to be the same. Derivative of the bottom, -1 over x squared, is the same as the derivative as negative x to the -2. We can use power rule. We get 2x to the -3. All right, by L'Hopital's rule again, we know that this original limit is equal to e to the x divided by 2 times 1. Let me rewrite this. So a way you could rewrite this is 2 over x cubed. Let's do direct evaluation. We get e to the negative infinity. Okay, no surprises there. 2 divided by negative infinity cubed. That's 0 over, oh, I see something in the chat. Yeah, cool. Okay, that's 0 over, all right, this is 2 divided by negative infinity. Again, that's just going to be 0. So we use L'Hopital's rule again. So at this point, you might be questioning, am I doing this right? Like, I just had to get L'Hopital's rule. We've already done it twice. Looks like we got to do it again. All right. The only thing that's changing each time is the denominator. And that power on bottom is getting bigger and bigger and bigger. So when we plug in negative infinity to whatever the denominator is, it looks like we're still going to get 0. So this was not the right way to go. Any questions on that? That is not the most easy, not the easiest thing to see.
Do you guys see that as you take the derivative over and over of the denominator, it's just going to get x to the third, then, or x to the negative third, then x to the negative fourth, then x to the negative fifth, and it's not going to end?
Yes, let me write it out this way. So these are the derivatives we've seen, but they keep going, right? And these all are just going to go to 0. As x approaches negative infinity. Good question, Alfonso. So at this point, we don't want to keep doing this forever. Start over. Try the flip with the other term. So we tried with x last time. Let's try with e to the x. So our original problem was x e to the x. And let's try the flip and put e to the x in the denominator. So now we have 1 over e to the x. Okay. When we use L'Hopital's rule, or rather, sorry, when we do direct evaluation, we get negative infinity on top. And 1 divided by e to the negative infinity gives us 0. Okay, so that's not quite gonna work. Let's try to rearrange this, right? Great, we can't use L'Hopital's rule like this. Another way to write 1 over e to the x, sorry, is e to the negative x. So let's try that instead. We get negative infinity on top. E to the negative infinity. Well, that's going to infinity. Aha, so we can use L'Hopital's rule again.
I have a question. Are we allowed to just say that 1 over 0 is infinity? Because that's what I've always, like, you can just say that 1 over 0 is considered infinity.
I think to be safe, you should probably put it in the other form. I don't know. That's
Okay,
what I was taught. It might work out that it doesn't matter, but I don't know for sure. So I would say if you don't get 0 over 0 or infinity over infinity, try to rearrange it. That way it's less to think about, you know? It's just less cases to keep in your head. Okay, so let's try L'Hopital's rule. The derivative of the numerator is derivative of x with respect to x is 1. Derivative of e to the negative x with respect to x is negative or rather it's this term times from chain rule, we take the derivative of negative x, right? This is chain rule right here. And so that gives us times -1. So we have negative e to the negative x. Okay, this is taking longer than I expected. We know that this limit from L'Hopital's rule is the limit as x approaches -infinity of derivative of x is 1 divided by derivative of e to the negative x is negative e to the negative x. Let's try direct evaluation again. We get 1 divided by negative e to the negative infinity. Okay. So that's 1 over infinity. 1 over infinity, that's going to be 0 for us. Questions on this one? So this is not unsolvable. We just took the wrong path to get there, unfortunately. Okay, so at this point, there are a few other tricks that we can talk about. We can talk about the natural log thing. What happened to 1 over x? Yeah, so we don't have 1 over x anymore. If we look up here, our original problem was x times e to the x, right? And we decided to start off by trying to put x in the denominator. That's where we got this 1 over x thing. But remember, we abandoned that that way of writing this because it wasn't getting us anywhere, right? We just kept getting another case of using L'Hopital's rule. And in fact, if we kept going, we would have done that forever. So what we decided to do was start over at this point right here. So we realized, all right, we're just going to have to use L'Hopital's rule over and over again. Let's try something else. So instead of putting x in the denominator by making it divided by 1 over x, we put the other part in the denominator, which was e to the x. So we got 1 over e to the x, which then became 1 over negative x. Is that okay? Doing okay, Hobby? All right, guys, so I have a bunch of problems here. I'm thinking, I know you like trig problems. I'm kidding. I know you don't like trig problems, which is the reason we should probably do one of those. Maybe we can get 2 done. Let's do this, and then I want to talk about another trick, but Mr. Bay already released a video on this trick, not the trig problem trick, but the other one that I really want to talk about. So if we don't get to it, he can drop that in the chat, if that's okay. So let's try another one. Let's do the limit as x approaches pi over 2 of secant x minus tangent x. Whoa, yeah, so this one's, these are 2 trig functions we are not used to using, or at least I'll speak for myself. I don't like secant. I don't even really like tangent. I like sine and cosine, keep it simple. If we were to graph these, which I don't want to spend too much time on, the way I graph these is take the graph of cosine, continues on like this, Secant is graphs like this. Right, because secant is 1 over cosine. Right, and we have these points here. This value, where we have an asymptote, is at pi over 2. So not only is this not defined, it's not infinity. It's not negative infinity, right? It goes to infinity when we come from the left, and it goes to negative infinity when we come to the right, from the right. With tangent, so this is secant x. With tangent, again, I don't really want to talk too much about this, but we have a similar thing where we have these asymptotes. This is a really poor drawing. But if you remember, tangent is sine over cosine. We have another asymptote at pi over 2. So this is just undefined minus undefined. Not even infinity over or minus infinity. What do? Well, we try to put it into a form that we can use L'Hopital's rule with. Rearrange, try to use L'Hopital. This is our strategy. All right, well, we already mentioned 1 over cosine is equal to secant, and tangent, same as sine over cosine. And in general, this is a good strategy to remember when you're doing trig stuff. When you're rearranging trig, put it in terms of sine and cosine. It doesn't always help you, but a lot of times it does. Okay, so here we had secant, tangent, we put it in terms of cosines and sines. We know how to deal with cosines and sines. Okay, if we try direct evaluation again, we can see that we get 1 over cosine of pi over 2, that's 0, minus sine of pi over 2 is 1, cosine of pi over 2 is 0. All right, this isn't really helpful. It's not 0 over 0 or infinity over infinity. So let's try to rearrange it yet again. So that limit is the same as, well, they both have a denominator of cosine. Let's put them together. So all I did here, I realized they had the same denominator. I put it as a single fraction. This is something you probably want to do in general, because the forms we're looking for are single fractions, right? They're not a complicated fraction minus a complicated fraction. They're both a single fraction. So in general, you probably want to try that. Okay, if we try direct evaluation again, we get 1 minus sine of pi over 2 is 1, divided by cosine of pi over 2 is 0. That's 0 over 0. Hey, let's use L'Hopital's. Okay, the derivative of the numerator, the 1 disappears. Derivative of negative sine is negative cosine. Derivative of cosine is negative sine. So by L'Hopital's rule, this limit is equal to the limit as x approaches pi over 2 of, instead of 1 minus sine x, we want its derivative, negative cosine x. Instead of cosine x, we want its derivative, negative sine x. Those negatives go away. Let's try direct evaluation. So we get minus cosine, I'll just leave the minuses for now. Minus cosine of pi over 2 is minus 0, divided by minus sine pi over 2 is minus 1. 0 divided by 1 is 0. So a trig problem. What are your questions on these? If you're like me, yeah, I was just gonna say, if you're like me, it's so much easier to see these and follow them than it is to think of what to do yourself. That's why I love this tip. Put in terms of sine and cosine. Again, can't emphasize this enough. It will not always help you. It will not always help you, but it does help you a lot of times. Like it did here. Yeah, so there's a thing called the helpful hexagon, which is also very helpful. It encodes a bunch of information about trig identities. That would be your plan B. You both, I think, are probably aware of the website Math is Fun by now. And they do a really good explanation of the helpful hexagon, or what they call the magic hexagon. Okay. Let's do a fun one. Let's do one that you can't really solve without doing this, or at least I don't know how to solve this another way. Let's do the limit as x approaches 0 from the right of x to the x. So remember, this plus means from the right. Okay, well, when we plug this in, we get 0 to the 0. That's not helpful. So what do we do? When we have, thank you for putting that in the chat. As long as we have, here, let's look up here for a second. We've dealt with e to the minus x a bunch, right? We've dealt with polynomials like x squared a bunch, okay? What do those have in common? Well, e to the x and x squared, the x is only in one place. It's either in the base of the exponent, like in a polynomial, or it's in the power in an exponential. Here, we have it in both places. That is not fun, okay? So when we get it in both places, try this trick. Let me write this out a little bit. When we have x's in both the base and the exponent, can't spell. Try this trick.
I think an easier trick would just be if you plug in directly and you get 0 to the 0 power or infinity to the infinity power. If you get a form that has an exponent to the 0 or to the infinity, then you know you're going to have to use this.
Okay. Yeah, I think it's the same. Good to think about it multiple ways, though. Okay. I don't know, this one's like, how do I want to explain this? If you remember from log rules, natural log of something and e to the x, natural log of x and e to the x are inverses. They're inverse functions. This has the nice property that when we do e to the natural log of some value y, they cancel out. Because of this inverse relationship. I already wrote this means, I don't need to write because of this. Okay, this is the key to the trick. So we are going to define y to be our function, x to the x. Then we have e to the natural log of y is equal to e to the natural log of x to the x. And from another exponent rule, or sorry, another log rule, this is the same as x natural log x, right? We can kind of take this and bring it down in front. Y'all with me so far? Okay. Yes-ish. Okay. Yeah, so we're just using exponent and log rules. Yeah. Okay. So we have this new function, right? But we didn't want this by itself. We wanted the limit as x approaches 0 from the right of x to the x, right? But we just defined this as y. We just defined x to the x as y. But from our little trick that we're using, we know that y is equal to e to the natural log of y. Okay, lots of pieces here. And we just found that this is equal to this right here. E to the x, natural log of x. So now this is our new problem we're working with. Does this look simpler? No, it looks much more complicated, but we can actually solve this. So since there's no x's here, this is actually equal to e to the limit as x approaches 0 from the right of x natural log x, right? Because e is just a constant, we can do this. It might look weird written like this, but this is actually what you're doing all the time when you're solving limits. You're constantly moving this limit. So let's ignore the e for a second. We'll come back to this. And let's just focus on that exponent. So the limit as x approaches 0 from the right of x natural log x. When we plug in 0, we get 0 times, all right, from the right, natural log of x approaching 0 goes to negative infinity. This is an indeterminate form. but it's not 0 over 0 or infinity over infinity. So let's try to put this in terms that we can, let's try to rearrange this so that we get it in the form of 0 over 0 or infinity over infinity. Let's use the flip. So this is equal to, same part right here. I don't know. I don't want to deal with a 1 over natural log of x in the denominator. So let's just move x to the denominator. So we keep natural log of x on top, move x to the denominator. Now when we plug stuff in, we get negative infinity still when we plug in 0. And we get 1 over 0. 1 over 0. Oh, I see. I think Mr. Bay was saying this before. 1 over 0 really is the same as infinity. You were saying that before, right?
It's tough for me to say anything because I never took the math theory classes, but I've always treated as any number over 0 is infinity, unless it's 0 over 0, which is indeterminate, or just, you know what, never mind. I never took the applied math courses in college, so technically it's considered undefined, but for our purposes, any number over 0 is considered infinity.
Yeah, you can think about this like we have a constant on top, just 1, and it's not really 0 on bottom. It's a smaller and smaller and smaller number on bottom. Hey, Trayvon. So as we have a smaller and smaller and smaller number on bottom, and the numerator is staying the same, the whole thing is getting bigger and bigger towards infinity. So now we have something in terms of what we can use L'Hopital's rule for. The derivative of the numerator, natural log of x, is 1 over x. The derivative of the denominator, I'm going to rewrite that in a form that I'm more comfortable with. 1 over x is the same as x to the negative 1. And then we can use power rule. Which is the same if we put it back as negative 1 over x squared. Okay, so by L'Hopital's rule, our original, well, not our original, our limit is equal to the limit as x approaches 0 from the right of, instead of natural log of x, we want 1 over x. Instead of 1 over x on bottom, we want negative 1 over x squared. Let's do some rearranging to get rid of this compound fraction. That's the same as take the numerator, multiply by the reciprocal of the denominator. Okay, we have negative x squared divided by x is x. When we plug in 0 from the right, we get 0. Okay, but remember, this is not the problem we want to solve.
There's Alfonso wants you to go over something again. I'm not sure what, but.
Okay, so just going to back up a little bit. If you have a specific part, please let me know. Mr. Bay, I'll turn it over to you after this, okay?
Yep, absolutely.
Okay, so yeah. Can I start from here? Okay, so we want the limit. We decide we want this limit from using that trick before. But when we use direct evaluation, right, we get 0 times natural log of 0 from the right is negative infinity. This is an indeterminate form, but it is not one that we can use L'Hopital's rule with. So we need to rearrange it a little bit, see if we can get it into a form that we can use L'Hopital's rule with. We already talked about this, like the flip. That's not a like real term, I just made that up. It's when we want to move one of these bits into the denominator. And the way we do that is we move the x into the denominator by making it divided by 1 over x, right? We saw that trick before. We try direct evaluation again. So as x goes to 0 from the right, natural log of x goes to negative infinity. And as x goes to 0 from either direction, 1 over x goes to 1 over 0. Right? This bit right here, we spent some time talking about. We just have a number divided by, it's not really 0, right? It's a number that's getting smaller and smaller and smaller on bottom. So when we have that, we have a number on top that isn't changing and a number on bottom that's getting smaller and smaller and smaller. So 0, we're approaching 0, right? Getting smaller, but this whole thing, because it's in the denominator, is going to approach infinity, right? If we divide by bigger and bigger and bigger numbers, sorry, if we divide by smaller and smaller and smaller numbers, our number is getting bigger and bigger and bigger, right? 1/2 versus 1, I'm going the other way again. If we start with 1/8, and then we go 1/4, 1/2, 1 over 1, I didn't mean to write equals, right? The denominators are getting closer and closer to 0, but our values are getting larger and larger, right? This is a really small piece of a pie. This is half of a pie. This is a whole pie. And then we have 1 divided by 0.5, which is 2, right? So I'm just trying to show you that as the number on bottom gets smaller, the whole thing, the whole value gets bigger.
If you divide 1 by 0.1, you get 10. If you divide 1 by 0.01, you get 100. If you divide 1 by 0.001, you get 1,000. If you divide 1 by 0.00001, a number very close to 0, you get 1,000,000. And so you keep on dividing by a smaller and smaller number. If you keep dividing by an infinitely small number, you will get an infinitely big result, at aka infinity. So any constant number divided by a number approaching 0 is infinity.
Yes, thank you. Okay, so yeah, key point here though, if we keep the numerator the same, then yes. Okay, so we can use L'Hopital's rule. Same thing as before, no surprises, right? Derivative of natural log x is 1 over x. Derivative of 1 over x, I rearranged that. I put it in this form using an exponent rule so that we can use power rule. And then I just put it back with the positive exponent. Okay, so then we use L'Hopital's rule. We don't want natural log x on top. We want its derivative, 1 over x. We don't want 1 over x on bottom. We want its derivative, negative 1 over x squared. And then I just flip the fractions and multiply. Right, this is just how you deal with a compound fraction. You flip the denominator and multiply.
Alfonso, are you caught up now? Are you... Okay.
Of course, yes. Okay, so, but this was not what we wanted to solve. We wanted to solve a much more annoying problem. X to the x. So I'm going to copy and paste this bit here. So let's do a quick recap, and then I'll hand it over to Mr. Bay for mean value theorem and extreme value theorem. We defined, nope, let's back up a little more. We started off with this as the expression we wanted to take the limit of, x to the x. I said, hey, let's just call that y. Okay. We have this relationship that since E and natural log are inverse operations, when we take E to the natural log of something, we just get the input back out, right? So E to the natural log of Y is equal to Y. I strategically named this Y because that's what we're using here. Okay, so E to the natural log of Y, which we know is just Y, is the same as E to the natural log of X to the X. But using a log rule, we can pull that exponent out front and multiply like that. Okay, so that's just a little bit of backing up to where we were at before. We just solved this bit using L'Hopital's rule.
We have to use this. We have to take the natural log of both sides because otherwise we can't get the exponent out. Otherwise we'd be stuck with an x to the x power. And we take the natural log of both sides so that we can use the logarithmic rule to move the x to the front so we don't have an exponent anymore.
So we found the limit as x approaches 0 from the right of negative x equals 0. That came from the limit as x approaches 0 from the right of x times natural log of x. We use L'Hopital's rule to get down here. But that's exactly what's in here. So this is from before or above. That's what we just talked about. From L'Hopital's rule, this bit, like I said, is equal to this limit, x times natural log of x, which is just the part in the numerator here. Not the numerator, the exponent. E to the 0 is 1. Ta-da.
So because we took the natural log of both sides, I did it a slightly different way than Mr. C. I did a video on this that I'll post in the chat right now on how to use logarithms to get an equation in the form that we can use L'Hopital's for. Basically, when I saw that we had an exponent, right, and so all of a sudden it's not in a form that we can use L'Hopital's for, I've realized, okay, if we have an exponent, I should be immediately thinking, take the natural log of both sides. And so we took the natural log of both sides, and then we evaluated it. And then at the end, we just have to remember that we did take the natural log of both sides. So now we have to put the answer to the e to the answer we evaluated because we have to cancel out that natural log we did at the beginning. Mr. C did it all, that showed that whole step at the very beginning. But if that's a little confusing, you can always just make sure that, okay, I'm going to take the natural log of both sides, and then you just have to remember at the very end to put that answer, your final answers to the e power, or e to the final answer is your actual final answer. It's pretty confusing, but I did a couple more examples on the YouTube video I just posted below. So if you are having trouble with that, once you see a couple of examples, it'll make a bit more sense.
Okay, you ready to talk about mean value theorem, extreme value theorem?
Yeah. Is everyone ready to go? Okay. Thank you for letting me know. So let's see. Okay. Okay, I'm going to go over MVT first, but there's actually a special case of MVT. So I'm just going to write down the problem first. So x squared minus 2x minus 8. Okay. So this problem specifically says Rawls theorem. Can you put in the chat if you've ever heard of Rawls theorem? Okay. Because we've had limited time because we're only able to have class twice a week. There's some things that you haven't had a chance to look at yet. Rawls theorem is the same thing as MVT. Okay? It's what MVT is based off of. It's MVT when the average slope is 0. So if you see Rawls theorem on the AP test, think MVT, right? You can do them the same way. And so I just wanted to introduce this term to you guys so you're not confused if you ever see Rawls theorem on the AP test. Okay? So if you plug in both -1 and 3, right? So the first thing you do with MVT is you have to figure out whether it's continuous. Okay? And because this is just an x squared function, we know that it's continuous from -1 to 3, so that's good. The only other thing that you have to do to satisfy Rawls theorem is that there has to be a slope of 0 from the line connecting the endpoint of -1 and the endpoint of 3. And so when you plug in -1, for any MVT problem, you need to find your endpoints first. And so if we put in f of -1, we need to find out what that is. And so when you put that in, you get 1 minus 1 plus 3. Or wait, I'm doing awfully on math. -5. My bad. Because it would be 1 plus 2 minus 8. So f of -1's -5. When we plug in the other side of the interval, so we plugged in -1, because that's one side of the interval. Now we need to do the other side, which is 3. So we get 9 minus 6 minus 8, which it is -5. Okay, so on the interval -1 to 3, we have the two endpoints. We have f of -1 is -5, and f of 3 is also -5. So this is a special type of MVT problem. You can solve it the same exact way as MVT, where the y values of both endpoints are the same. So you look at it on the graph, right? You got -1, right here is one endpoint, and then you go forward 3. This is the other endpoint. The average slope between these two is 0, because they have the same y value. Are you guys following me so far? Trayvon, Javier? Okay. So the whole thing of what MVT is basically we're trying to find the average slope between the two endpoints, which we just did. We found out because it's Rawls' theorem, the average slope happens to be 0 in this case. And so we need to find where on this graph, we need to find out where on this graph the slope is equal to the average slope. Okay, and in order to do that, we have to find out the equation of slopes for f of x. Let me put this back to green. Right, this is our f of x. And we know on the interval -1 to 3, the average slope is 0. And so we need to find out, okay, where is the slope 0 for x squared minus 2x minus 8 on this interval? And to do that, we have to take the derivative to find the equation of slopes. Okay, so when you take the derivative of x squared is 2x. Derivative of -2x is just -2. And derivative of -8 is 0. So this is our derivative. And because we want to find out where the slope is 0, we have to set our slope where f prime of x equal to 0. So 2x minus 2 is equal to 0. We get 2x equals 2, and then x equals 1. So you have to be careful, because sometimes you'll get multiple x values. And you have to remember, well, it has to be in this interval. And so is x equals 1 in this interval? Yeah, it is. It is between -1 and 3. And so, let's see. So our answer is x equals 1 for this one. Okay, that's our answer. So when x equals 1, that is when the average slope, that is when the slope is equal to 0, which is equal to the average slope of the interval. We're just reviewing EVT and MVT. I only brought up Rawls' theorem because you guys never did it in class, but it's the same thing as MVT. So if you see Rawls' theorem on the AP test, just treat it like MVT. It just happens to be a special case of MVT where the average slope is 0. I'll go over another MVT where it's not Rawls' theorem. So let's see. Okay, let me find another problem. I think I've actually gone over this problem before. Okay, we're going to do another one. I'm going to erase this. Four z cubed minus 8z squared And so we're going to do MVT on the interval 2 to 5. Okay, so first thing we have to do here is we have to determine whether this function is continuous on the interval 2 to 5. Well, you can see that it's just a cubic function, so it will be continuous. And now we have to figure out, in order to figure out where on the graph it's equal to the average slope from 2 to 5, we first have to figure out what the average slope is from 2 to 5. So we need to evaluate f of 2 and f of 5, find the point, and find the average slope. So we need to find the endpoints. So the first step for MVT, figure out if it's continuous, and we can even use MVT on the interval. Second step, you need to find both endpoints. Okay, so we're going to find the endpoints. So we'll start with f of 2. You get 4 times 2 to the cubed minus 8 2 squared plus 7 times 2. So 2 cubed is 8 times 4 is 32. Minus 8 times, well, 2 squared is 4. That's also 32. 7 times 2 is 14. And so 32 minus 32 cancels, and you get 14 minus 2, which is 12. So 12 is equal to f of 2. So we have our first endpoint on our interval. We need to find the other endpoint. Let me know if if anyone gets lost, or if you feel lost, and I can explain things more clearly. 5 cubed is 125. 4 times 125 is 500. And let me know if I do my math wrong too. 8 times 25 is 200. So we get 333. So we figured out our two endpoints on this interval. So we have some cubic function, right? And we figured out our two endpoints. We have an endpoint here and an endpoint here. We have 2, 12, and we have 5, 3, 33. Just because when I plugged in 2 and 5, I get this on the graph. And so what we want to find next, after we find our two endpoints, is the average slope between the 2 points. We want to find the average slope of the line between the 2 points. Okay? And so to do that, we just have to take rise over run. So let's see. We take our y values, 333 is our one y value, and subtract the 12. And then we divide it by our change in x values, right? Change in y over change in x is equal to slope. And so our change in x values is 5 over 5 minus 2. And then from there, 333, 321 over 3 is our slope. And then when we divide that out, we get a slope of 107 is equal to our slope. Does everyone get how I got the slope, the average slope between the 2 points? Can I get a 1 through 3 in chat of if everyone's good to go or not? Or if you have some questions, you might be at a 2, or if you're completely lost at a 1. Actually, I should put average slope on the interval 2 to 5. So 107 is our average slope on the interval 2 to 5. And so now to satisfy MVT, we have to take the derivative to get our equation of slopes and find where on the interval is it equal to 107. So we have to take the derivative here, get our equations of slopes. So when we take the derivative, so derivative of 4z cubed is going to be 12z squared. Derivative of 8z squared, or negative 8z squared, would be 16z. And derivative of 7z is going to be 7. And because we have to find where the slope's equal to the average slope on the interval, we have to make this equal to 107. Okay, and so from here, we just have to solve. And since we have a quadratic equation, there are numerous ways to solve quadratic equations. However, not all of them will work all the time. This is why I always suggest using the actual quadratic formula. And I know not everyone's learned that, but if you're going to want to learn how to factor every problem, you're going to have to learn the quadratic formula, negative b plus minus square root of b squared minus 4ac all over 2a. a lot of you probably are familiar, but some might not have learned that. Let's see. So first, let's just solve this equation. Okay, from here, we want to make it so that it's 0 on the one side, so we can actually use the quadratic formula. You get 12z squared minus 16z. You subtract 107 from both sides, so you get minus 100 is equal to 0. And normally we'd try and get into a form where we would have z minus two numbers is equal to 0. And I'm trying to, let's see. For this particular one, a lot of the ways won't work, so I'm going to use the quadratic formula because this one always works. So quadratic formula is if you have a function, if you have a function like we have here, 0 equals ax squared plus bx plus c, then the quadratic formula is x, your x values are going to be equal to negative b plus minus square root of b squared minus 4ac all over 2a. And that'll get you the x values that you'd normally, or I guess z values in this case. So our a is 12, right? Our a is going to be 12 here. Our b is negative 16. And our c is negative 100. I know when I went over this before, some had not seen quadratic formula, but some have. So let me know if you've seen this before. Have you guys seen quadratic formula before? Okay. When you plug this in, yeah. So unfortunately, this is going to be the only way to solve this one. You can't really use square rule for this one, or like completing the square or anything like that. So, like I said, a is equal to 12. B is equal to negative 16. And C is equal to negative 100. And so when you plug that in, you're going to get Z is equal to negative B is negative 16. So you're going to get positive 16 plus minus B squared. So 16 squared, or negative 16 squared, minus 4. And so A is 12. C is negative 100. And then all over 2a, which is a is 12. So 2 times 12. To save time, I'm not going to calculate this all out. The answer we get from plugging that all in is 2 plus minus, I'm going to put this, let's see. The answer we get, or I guess it's Z. Yeah, what Mr. C is correct. We get a plus minus, so we're going to get two solutions. Just like how we normally would get. With a quadratic formula, there's going to be two x values or two z values. So we're going to get 2 plus minus square root of 79 all over 3. And this is what we get when we simplify this expression. So if you actually calculate this all out, that's what we'd get. Just double checking that's right. But we have to remember, we have to figure out, is it actually in this interval? So we know that, well, okay, we get 2/3. So what this is equal to, because we have two solutions, we have 2 plus square root of 9, square root of 79, all over 3 as a one solution, and then 2 minus square root of 79, all over 3. But 2 minus square root of 79, it's the same thing as 2/3 minus square root of 79 over 3. That's not going to fall in this interval. When you actually calculate this out using a calculator, you'll find that it's not actually in this interval. And so that's not an actual answer. This does fall in the interval of 2 to 5, so this is your answer. This is equal to about 3.6, which is between the interval 2 to 5. So Z is equal to 2 plus square root of 79 over 3. That is where it's equal to the average slope of 107. And this one is not a valid answer because it doesn't fall in the interval 2 to 5. Okay, so those were my examples for MVT, and I was going to do a quick example for extreme value theorem, EVT. You guys have any questions on that one? Quadratic formula is just something that if you want to solve a couple of these, you're going to have to memorize, but I wouldn't put a priority on it if you don't know it. Okay. I will move on to EVT if there's no questions on this. Can I erase the board here? Okay. Okay, so let me copy down this next one. There was only two solutions in that problem, and only one was in between the interval. So there was only the one solution was right. Oh, I accidentally started copying down the wrong problem. This last one will be quicker. Okay, so EVT is a little bit different than MVT. You still have an interval, right? So in this case, the interval is -2 to 1. So from this point, what EVT is asking you to do is find the absolute extrema, which means the min and the max, right? And so what you have to remember, the trick with EVT, let me just write it. Extreme value theorem. The trick with extreme value theorem is you just have to look at it. It says extreme value, right? So we are looking for the extremes, either the min or the max. So if this is -2 to 1, right? I don't know what the actual graph looks like, but if you have any particular graph, right, and it's asking from -2 to -1 to 2, right? It might be that the extremes on the endpoint, this is the highest point. So it's not just the case of looking for like the local max in the interval, we have to test the endpoints as well. Okay, so the first step is to try and find any critical points on the interval, and to do that, we have to take the derivative first. But just remember, at the very end, we have to test the endpoints as well. Okay, so when we take the derivative first to find any critical points, look for any local maxes or mins, we take the derivative, and derivative of 4z cubed will be 12z squared. Derivative of 3z squared is going to be 6z. Derivative of 9z is 9. Okay, and so we have to find the critical points, which means we have to determine when the slope's equal to 0. Because if there's a local maximum or minimum, the slope on that critical point is going to be 0. So again, we have a similar equation where we have a quadratic, and we have to find out what z is equal to. A is equal, we're going to have to use a quadratic equation again. A is equal to 12. B is equal to -6. And C is equal to 9. So we're going to have to use the quadratic equation again. And the quadratic equation doesn't change. It's just something you'd have to memorize. Okay, and so you have to plug in for each, right? Because, again, we know that 12 is A and -6 is B, because this is the form that the formula takes. And this is how you use the quadratic formula. So when we plug in, we get negative times -6. -6 squared is 36. Minus 4. A is 12. C is 9. And then 2 times A, 2 times 12. We get 6. Again, plus minus implies there's 2 solutions because there are 2 solutions to a quadratic equation. 36. 4 times 12 is 48 times 9. I need a calculator for that. I believe it's 432. All over 24. And we get 6 plus minus 396. Negative 396. Okay, so this is where we kind of come across a trick. Let me write it so it's more clear. We get a negative under a square root. Does anyone know what that means? Is it possible to have a negative under a square root? You can't evaluate it, right? Thank you, Javier. We end up getting an imaginary root, and this is another reason why you have to use quadratic. A square root of a negative number is imaginary. And if we were to evaluate this, we would end up getting, all simplified down, 1 plus minus, let's see, square root of 11i. All over 4. And I is equal to the square root of negative 1 because it's imaginary. It doesn't exist. And because the extrema of this does not exist, this isn't an actual answer. So we see that when we get this as an answer of using quadratic formula, the roots of z are imaginary, then the answer doesn't count, and there are no critical point. There aren't any local mins or maxes on this interval. Well, actually on the function itself. And so what we have to do is, because we still want to find the extreme values on the interval, is we can test the endpoints. So now what we're going to do is we're going to find f of negative 2 and f of 1 of the original function. We're going to plug, or h of 2 and h of negative 2 and h of 1. So we're going to plug in h of negative 2 and h of 1. And from there, let's see. So when you plug in h of negative 2, and then h of 1, we'll get our 2 endpoints, and we'll find out which one's the max and which one's the min. Just by determining their y values. And so what do we get for this? Negative 32. Minus 12. Minus 18. We get negative 50. The 12s cancel out. And then h of 1 and from there we get 4 minus 3 plus 9 plus 12. 21, 18. And we get 22. So h of negative 2 is negative 50. And because there was no local mins and maxes on the interval, we just look at our endpoints. And so our local minimum is negative 50 is the point. Our answer is negative 2, negative 50 is our absolute minimum on the interval. And our absolute maximum is 122. That's our absolute max. Because 22 is the highest value, negative 50 is the lowest value. And that's extreme value theorem. The most important thing to remember for extreme value theorem, finding all the mins and maxes, is you do it normally where you try and find your critical points on the interval. And but you have to remember to test the endpoints. Because you could just have a function. You could have a function where it's just a straight line. For instance, as a quick example, you could just have a function that's a straight line. And these are not going to be critical points, but this would be your local min or absolute minimum on the interval, and this would be your absolute maximum. So you have to remember to test the endpoints for extreme value theorem. Any questions for me? I went a little bit over, so my apologies. How do we feel on this, like 1 to 3? I showed you this imaginary root here, just to let you know that if you do get something like a negative under a square root, don't panic. But for this purpose, we don't consider it. I just didn't want you to like panic if you saw this on the test and you didn't know what to do. So just ignore the imaginary root for something like EVT or MVT. Okay, so we just cancel this out. Or not cancel it out, we ignore it. Are you guys still with me?
Where'd everyone go?
Javier, Trayvon, Edwin. So this is why we ignored them. We're operating in the real world. We just ignore the imaginary number when it comes to stuff like this. So if you do get something like this, and like I said, the only way you're going to be able to factor this is through quadratic equations. So you're going to want to learn this. Do you guys get how I put in how I figured out what A, B, and C are? Can you guys give me some? Do you guys get how I figured out that A is 12, B is -6, and C is 9? Right here. Okay. Okay. I think the teacher that's hosting this needs to go, so we're gonna wrap it up here. But thank you guys for coming.
Yeah, thanks everybody. We'll be doing this again tomorrow. We'll be talking about related rates. And I think that's related rates and describing graphs of derivatives and stuff like that.
Okay.
Okay. Bye.